Hello everyone. This module will be all about Coulomb's law. This is a follow-up module on our last one regarding electrostatics. I just divided this video into two parts. First will be the concepts, and then eventually, towards the end of the video, we will be solving a few problems with regards to Coulomb's law. So let's start. So let's just review a little on electrostatic force. We always encounter two words, repel and attract. So the act of repelling implies pushing, and the act of attracting or attraction suggests pulling or towards each other. A push or a pull pertains to force, and we know that an electric charge exerts a force on each other as they interact. So basically, when you talk about Coulomb's law, we'll be getting the forces between charges, and it's a very simple formula. Later on, I will be introducing it to you. And here it goes. For electrostatic force, this is actually the force that comes from the attraction and repulsion between electric charges. And the formula is straightforward. It's F equals KQ1 Q2 all over R squared, where F is your electrostatic force, Q1 and Q2 are the magnitudes of the charges, R squared is actually the distance between charges. Actually, it's R, but in the formula, R squared is used, and K is the Coulomb's constant. And this was conceptualized by Charles Coulomb in the 1700s. His full name is Charles Augustin de Coulomb, if I'm not mistaken. He experimentally established the fundamental law of electric force between two stationary charged particles. His major contribution to science, of course, will be this one in the field of electrostatics and magnetism. However, during his lifetime, he also went into the study of strength of materials and structural mechanics. And we go back to Coulomb's law. We have to understand how the law works, or what are the different properties of an electric force in relation to the law. So an electric force has the following properties. First, it is directed along a line joining the two particles and is inversely proportional to the square of the separation distance r between them. Because if you remember, I think a few slides ago, or a couple of slides ago, it simply is F K Q1 Q2 all over r squared. So basically, it says it is actually joining the two particles Q1 and Q2, and it is inversely proportional to the square of the separation distance between them. It is proportional to the product of the magnitudes of the charges Q1 and Q2 of the two particles. It is either attractive if the charges or repulsive. It's attractive when the charges are of opposite sign, and repulsive if the charges have the same sign. And there is a value, or there is a constant that we have to consider, and that is actually our K. And that's called your Coulomb constant, or sometimes Coulomb's constant. But make sure that you just know the value of K. And its value is actually here. The K, or the Coulomb's constant, is 8.9875 times 10 to the ninth Newton meter squared over Coulomb squared. Or for simplification of solution, we can actually use 9 times 10 to the 9 Newton meter squared per Coulomb squared. You can do that. And for simplification of solution, I will be using 9 times 10 to the ninth all throughout the solved problems I have for Coulomb's law. Let's just go back to this. I might have missed something. Okay. It says here electric forces between unmoving objects or charges are called electrostatic forces. For moving charges, we create magnetic forces. So let's go to the other constants or other values that we might encounter. For the charge of the proton, It is usually 1.6 times 10 to the negative 19. Therefore, it would take 1 over E, or that is around 6.242 times 10 to the 18 protons to create a total charge of 1 coulomb. Likewise, since the E value or the charge value is the same, likewise 6.242 times 10 to the 18 electrons would have a total charge of negative 1 coulomb. Basically, for the charge, they are the same in value, except that your proton is positive and your electron has a negative charge. And these are usually some values that might be useful for our computations. So we have here the three subatomic particles. We have your electron, your proton, and your neutron. They have their charges. We said a while ago that the electron gets a negative charge, the proton has a positive charge, and of course a neutron, it is not a charged subatomic particle, so that's zero. And for masses, we can see here that the electron is fairly light as compared to the proton and the neutron. These are heavier than the electron. And when you're using it, when using Coulomb's force law, remember that your force is a vector and must be treated accordingly. So it follows law of sines, law of angles. You have to plot them properly on the Cartesian coordinate system, and you will be solving them not algebraically but via vector addition. The picture on your right will show the electric force of repulsion between two positively charged particles. We said that, for example, in this case, this is positive, this is positive. The tendency of the two particles will be to repel or to go against each other or pushing. Well, when they're positive, negative, like in this case, this is positive, this is negative, they have a tendency to be pulled together or pulled inward, and that is the force of attraction. And like other forces, electric forces obey Newton's third law, meaning hence the forces F12 and F21 are equal in magnitude but opposite in direction. From Newton's third law, F12 and F21 are always equal, regardless of whether Q1 and Q2 have the same magnitude. Yes, they have the same charge, they have the same value. It's just that um, when it comes to direction, they will be opposite each other. It's F12, meaning this is the force of 2 with respect to 1, and this is F21. This is the force of 1 with respect to 2, or 2 to 2. Okay, since this is Q1, outward would be the sign designation. So if it is affected by Q2, it's F2. It's the force of 2 reacting to 1. And here also F12 is the force of the effect of 1 on 2. So again, in the naming convention, outward in the subscript, the one outward will be the charge reference. Okay, so let's continue. 2-point charges separated by a distance r exert a force on each other given by Coulomb's law. The force on Q1 is equal in magnitude and opposite in direction to the force on Q2. So of course, again, just to repeat it, when the charges are of the same sign, the force is repulsive, and when the charges are of opposite sign, the force is attractive. And it is also similar to your gravitational force. Both act at a distance without direct contact. Again, they don't have these are non-contact forces. Both are inversely proportional to the distance squared, with a force directed along a line connecting the two bodies. And they only have a few differences, two important differences between Coulomb's law and gravitational force. Electric forces can be either attractive or repulsive, but gravitational forces are always attractive. The electric force between charged elementary particles is far stronger than the gravitational force between the same particles, as the next example shows. So we have already discussed this previously. So again, if one is positive, the other one is negative, this is attractive. Let's just change my, this is attractive, okay? And this is repulsive. Very easy to remember. And as a summary, as charges move farther to each other, then the electrostatic force between them weakens. As they move nearer each other, the force strengthens. And I think this is best discussed by illustrating some examples or word problems for our examples, just to strengthen it. Okay, so for the first example, what is the electrostatic force of attraction between negative 6 times 10 to the negative 6, or I think that's 6 microcoulomb charge, and a 4 microcoulomb charge if they are separated by a distance of 3 meters? What's important is for you to get a Newton. Okay, I must just change a tip. I think it's very wide. For you to get a Newton, when it comes to your force, your distance should be in sorry, not cm, it should be in meters, and your charge should be in coulombs. Okay, just to get a Newton in our unit of force. So let's solve the first. Usually what do? We just get the given. So Q1 here is equal to negative 6 times 10 to the negative 6. Coulomb Q2 now is, I think that's 4 times 10 to the negative 6 coulomb. You have a distance of r, which is 3 meters. No need to convert anything, simply because everything is consistent. So required here is the force. We're looking for the force. It's a direct application of the formula. That's K Q1 Q2 all over R squared. So this is K. As I've said earlier as well, I'll be using 9 times 10 to the 9, and then negative 6 times 10 to the negative 6, and 4 times 10 to the negative 6 all over. No need to convert anything. So this is 3 squared, and I'm supposed to be getting a force value of, I already listed my answers for this, and maybe you can try it on your calculators. Also, for the benefit of not to lengthen the video too much, as I already solved this beforehand. So this is now equal to 0.0224 newtons. Okay, it's as straightforward as that. Just substitute it into the formula that was given, and then be consistent with your units, and then of course just solve it. Okay, let's have example 2. Two identical charge 1 peso coin are 1.5 meters apart on a table. What is the charge of one of the coins if each of them experience a repulsive force of 2 newtons? Again, this is just an application of the two charge Coulomb's law. So we have at the onset, we can see that we have R, which is 1.5 meters. The problem is saying two coins, identical coins. So we can say that Q1 is equal to Q2. And for simplification later on, we can use Q so that we don't have to convert later on. So we're looking for the charge because we will be looking for that value. F is also given, which is 2 newtons. So what do? K, if you just want to list it, 9 Newton meter squared per coulomb squared. And we're looking for the Q value. And again, we use our Coulomb's law formula, KQ1 Q2 all over R squared. But since Q1 is equal to Q2 and we said that they're also equal to Q, you can say that F is KQ squared all over R squared. And we're looking for Q. By simplification, you can get Q as the square root of F r squared all over K. And we substitute. Our Q now is equal to the square root of 2 times our R is 1.5 squared all over K, which is 9 times 10 to the 9. And I'm getting Q, which is equal to, this is what I got. You can validate it using your own solutions. You can solve it using your calculators. I got 22.36 times 10 to the negative 6 Coulomb. This is also equal to the value of Q1. This is also equal to the value of Q2. So this is my answer. Okay. Should you have questions, just let me know. You can message me, um, or you can chat or comment on the video should there be errors in the digits or computation. Let me just do an undo. Okay, because I think I covered the negative 6. So there you go. Let's just make this here. Okay, it's perfect now. Okay, that will be example 2. Again, what made me decide that I will be using the same Q, or I could um, assume that Q1 is equal to Q2 simply because from the term identical, it means that Q1 is equal to Q2. So let's have example 3. The examples are quite similar to each other. It's just really practice, especially in the use of exponents. You might get errors in the final answer simply because of the exponents or the prefixes used in the problem. Okay, example 3. We have compute the force for the force of attraction between a 1.6 times 10 to the negative 19 Coulomb charge and a 2.09 times 10 to the negative 18 Coulomb charge if they are 4.01 times 10 to the negative 10 meters apart. Okay, let's solve that. Okay, that's a Q1 now is equal to 1.6 times 10, negative 19 Coulomb. We have a Q2, which is negative 2.09 times 10 to the negative 18 Coulomb. And R is just a play on the prefixes or exponents times 10 to the negative 10 meters. And what are we looking for? We're looking for the force of attraction. So we're looking for F. So straight out, F is equal to K Q1 Q2 all over R squared. So my F now is equal to 9 times 10 to the 9. Let's just insert it there. 1.6 times 10 to the negative 19. And then negative 2.09 times 10 to the negative 18 all over 4.01 times 10 to the negative 10 squared. And my solve value for F is 18.72 times 10 to the negative 9 Newton. So if please just validate it using your own computations, and then should there be again errors in the digits, please message me or you can comment on the uh, video below. Okay, let's have example 4. It says here that it's actually the same, so you can do it this on your own. Again, for this problem, you will be getting the force, repulsive force now, and you should be getting, I won't be solving this anymore in this video because I still have one longer problem to solve in a bit. So you should be getting an answer which is F is equal to 3.32 times 10 to the 32nd power Newton. Maybe you can just do this on your own for practice, but I give you the answer. And for example, 5, I think I also solved this a while ago. Yes, it's in my cheat sheet in front of me. So here you're looking for Q, which is basically the same as your approach with example 2 a while ago. And you should be getting a Q, which is equal to 26.45 times 10 to the negative 6 Coulomb. This is also equal to your Q1 is equal to Q2. What you do here is just apply again the Coulomb's law formula. Be careful, or be yes, be extra careful with your units, because that's where you might get the error, since the formula is quite simple. And of course, before I end the video, I have one problem here. I'll be solving a 3-charge configuration in a right triangle. Okay, so let's see. It says here 3-point charges are fixed in place in the right triangle shown below, in which Q1 is equal to 0.71 microcoulomb and Q2 is equal to negative 0.67 microcoulomb. What is the magnitude and direction of the electric force on the 1 microcoulomb, we can call this Q3, charge due to the other 2 charges? So it says here that we can call this Q3. Our Q1 is 0.71 microcoulomb. Our Q2 is negative 0.67 microcoulomb. So what's important in formulas like this will to be identify the distance between the charges as well as the position of the charges. We have an hypotenuse here that says that's 10 centimeters, so we can actually solve this and this, which are equal. Since this is a right triangle, I can say that this is 45 degrees, and this is also 45 degrees. So let's solve for this one. So we can call this R13, since I also need the distance between Q2 and Q3, because it says here the reference charge will be Q3, so I can solve for this. We're solving for R23. And from our Pythagorean theorem or law of trigo functions, we can solve for R23. How do we do that? You can do a lot of things. You can solve it on a lot of ways. But the easiest, I think, would be sine. So kat Hova, remember? It says there that sine 45 is equal to R23, right? All over R13. So we can say that R23 is equal to, you can just say that that's 10. Wait, R23 is R13 sine 45. So R13 is 10 centimeter times sine 45. This I haven't solved yet. So you might be hearing my calculator every now and then. So this is 5 squared of 2. So that's 7.07 cm. So we already have the basic info that we need to continue solving the problem. And as I've said, there will be 2 forces. That will be 1 on 3 and 2 on 3. And let's just solve them using Coulomb's law. Okay, so that's F, I said 1 on 3. That's K, Q1, Q2 all over R13. Let's just be consistent. So F13 now is equal to 9 times 10 to the 9. Q1 is 0.71 times 10 to the negative 6. And this is 1 times 10 to the negative 6 all over R13. That's 10 cm. So that's 10 times 10 to the negative 2 squared. My F13 now is equal to, let's check that. It's 9. I haven't really solved this a while ago or today. times 0.71 to the negative 6. You can, I guess, compute it with me, even if you're just watching the video. Negative 6 equals all over 10 to the negative 2 squared. So this is 0.639 newtons. Okay, keep that handy. Just park that. Okay, that's F13. And later on, we will identify the direction of that later on. Let's just park it. Let's add another page, maybe a blank sheet now. Now we're also going to solve F23. F23 is K Q2 Q3 all over R23 squared. So that's 9 times 10 to the 9. Q2 here is 0.67. Okay. Oops, so you can see that there's an error here that should be squared. Okay, I'm correcting that. And then, I'm sorry, that's negative 0.67. Negative 6. Then we have 1 times 10 negative 6 all over. It says 7.07, so that's 7 times, oh, sorry, 7.07 times 10 negative 2 squared. So my F23 now, they're very important that you solve them. Okay, so that's 9 to the 9 times 0.67 negative 6 times 1 negative 6 all over 7.07 is a negative 2 squared. Okay, I'm getting 1.21. So that's 1.21 newtons. Okay. Okay. So most of the info that you need to be able to solve the resultant or the resultant force, yes, at Q3 is already in place. All you have to do now is use vector addition. So let me just move this a little. Let's just move it. I think I have a select tool. Where's my select tool? I would want to move this a little. Let me just move this, okay? So that I don't have to like, there you go. Moving that, as I've said, I'll be using vector addition, but we have to study the direction first. So usually what I do is I will plot them in the Cartesian plane. I'll be plotting. My reference is Q3, so this is my Q3. My Q3 is at the center. And we can see that this is positive, Q1, this is also positive. So where will Q3 go? Q3 will go away. It will go away. The effect of Q1 on 3 will be repulsive. Q1 will also go away. And Q3 will definitely go the other side. So Q3 here. So this is now your F13. This will be the force of 1 on 3. And since this is also 45 degrees. Now we go to the other one. What about this one? So where will Q3 be going? This is negative, this is positive, so it's going toward Q2. Therefore, I can plot it here. Let me just do that again. I think that is a skewed line. So it's going to be going here. This is now F23. It's going to approach Q2. So this is now your basis for your vector addition. So if you remember our vectors, if you remember in the laboratory, we had let's say F13, we have F23. You can, of course, resolve the vectors on the way that you are familiar. I'm more familiar with tabulating them. So this is X, This is y. So this is now f13 cosine. And f13, that will be 270 plus 45. That's 315. And then this is f13 sine 315. And my f13 is, let's write that. My f13 is 0.639. So that's, okay, let's put that here. 0.639 cosine 315 and 0.639 sine 315. Just for discussion purposes, so that on the other fours, we don't have to write everything. 0.639 cosine 315, we're getting 0.45. Okay, 452. And take note, it should be, yes, it should be a positive x but a negative y. Maybe. Let's see. So my 0.639 uh, sine 315 is equal to, there, it's correct. It's negative 0.452. Okay, now you'll be using f23. This is now equal to 1.21 cosine 180 and 1.21 sine 180. You know that cosine 180 is negative 1, right? Let's check that. Cosine 180. So it's actually negative 1.21. And our other value, I know that sine 180 is what? It's equal to 0. Because also, you can see it from the figure, there is no y component. It's only lying on the x. So this is now 0. And then eventually, if you remember my method in the laboratory, we just sum it all up. So 1.21 minus 0.452, we're getting negative 0.758, and this is negative 0.452. We're not yet done because those are only the components of your summation. So to be able to get the f net, or the f3, will be the Pythagorean theorem. It will be the summation of x, so fx squared plus fy squared. F3 now is equal to, so that's negative 0.758 squared plus negative 0.452 squared. And looking at it, the position, or the resultant will be on the third quadrant because both of them are negative. So f now is equal to, let's just solve that, 0.758 squared plus 0.452 squared is equal to, and then we get the square root of that, we're getting 0.88 newtons. So that is F3, but that's only the magnitude. And where is it located? You can do a tangent function. Okay, theta is equal to the tangent negative 1 of Fy over Fx. It's tangent negative 1 of Fy negative 0.452 all over negative 0.758. Our theta now, I'll just write theta here. Hopefully it fits. Okay, that's inverse tangent. Let me just get my inverse tangent. Okay, and that's negative 0.452 and negative 0.758. And let's just, almost done. So the answer is 30.81 degrees. Okay, now I'll be solving this problem. I'll cut this video for now. I'll just provide another example in a bit. But for now, this is how Coulomb's law works. We started with, of course, the concepts. What is Coulomb's law? And then Again, the summary will be as charges move farther from each other, the electrostatic force between them weakens. So the farther they are, the weaker the force. And then, of course, there were different problems solved to illustrate the use of our Coulomb's law. Okay, for now, I'll leave you with our last problem, and then I'll just be giving another one in another video. Okay, hopefully this helps you in your review, and till the next video, thank you.